so we can get as many people in the house as we can. I'm going to ask that everyone take a seat because we're going to get started in a few seconds.
Carnegie scientists explore the outermost reaches of space, the mysterious depths of the Earth, and the origins and mechanisms of life. Our brilliant and dynamic teams of scientists transform the landscape of discovery with their unbridled passion, insatiable curiosity, and never-ending quest for knowledge. With limited teaching, administrative, and grant pressures, Carnegie's scientists concentrate on research and are empowered to go their own way. Our scientists are chosen for unique skills and boldness. Their amazing discoveries, spanning more than a century, demonstrate the power of freedom. Carnegie astronomers, astrophysicists, and planetary scientists are committed to finding answers about our universe. From the expansion of the universe, discovered by Carnegie's Edwin Hubble, to the chemistry of stars and the diversity of exoplanets, Carnegie's distinguished investigators probe distant reaches of space and time. From curiosity comes discovery. Geophysicists, geochemists, and ecologists use cutting-edge instrumentation in our laboratories and venture out to nature's laboratories, stunning rainforests, ancient rock formations, flowing lava lakes, and beckoning coral reefs. They explore Earth history and dynamics with passion and determination, unprecedented independence from short-term pressures, close collaboration, and interdisciplinary approaches set Carnegie scientists apart. Taking risks and using new approaches, their findings have critical implications for understanding Earth's properties and guiding policy. Carnegie scientists make outsized contributions to unlocking the secrets of life and laying the foundation for improving it. Carnegie's Nobel Prize-winning Barbara McClintock made discoveries about chromosomes that completely changed biology and medicine. With latitude to undertake long-term, higher-risk projects, our researchers investigate the molecular basis of life, from computation and genomics to advanced microscopy and engineering, to remote sensing tools and forest canopy fieldwork. We construct a clearer picture of plant, animal, and microbial life, diverse ecosystems, and changes driven by human activities. Carnegie investigators are intrepid adventurers who pursue their goals even as they mentor and train the next generation of scientists. They are free to question, to wonder, to creatively pursue ideas from the vast universe to the subatomic world. Our scientists redefine the pursuit of what's possible for us, our planet, our universe. We explore the past to understand the present and inform the future.
Welcome, everyone. Thanks for braving a little bit of weather to come here. Let's start with another little video. Hi, I'm Matthew Scott. I'm the president of the Carnegie Institution for Science, and today I have the privilege of visiting the ALMA radio telescopes here in the Chilean Atacama Desert. We're at about 5,000 meters of altitude here, and on this mountaintop plateau, as you can see, there's this incredible array of 66 of these giant radio telescopes. These each weigh about 120 tons. And they are moved around like chess pieces on this mountaintop to any of 200 different locations. By spreading them out, the telescopes get higher resolution in their signals, and by concentrating them, and today they're all concentrated here, you get higher sensitivity. So I'm starting to learn a few of these things, even though I'm not an astronomer, by listening to our wonderful hosts here, Pierre Cox, who's the director, and his team, who have brought a Carnegie group to this mountaintop today to see ALMA. Once in a while you lose one of them. They're called back. All right. So let me tell you a little more. It was such a fantastic time visiting that mountaintop, and Pierre was such a wonderful host, and our dream of that moment was to bring him here for one of these lectures, and now he's here with us. So it's really great. So let me tell you some background, much of it new to me and perhaps to you. In 1932, a young Bell Laboratory scientist named Carl Jansky was tasked with finding the sources of static interfering with transatlantic telephone calls. What he found instead with the rotating antenna system that he set up in a New Jersey potato field was the first extraterrestrial signal from radio waves, what he called star noise. Jansky's discovery would transform astronomy, but not right away. Though the New York Times carried a front page article about the discovery, and NBC actually broadcast the signal for all to hear, it took more than 20 years for astronomers to realize that star noise has a lot to say, or someone has a lot to say. The history of radio astronomy since then has been one of increasingly larger and more sensitive instruments designed to catch the cosmic noise of radio waves. The signals are weak. Radio waves are longer than the waves of visible light and carry less energy. So the antenna ears of a radio telescope are, as you saw, huge. The total resolving power of the 27 linked dishes of the Carl Jansky Very Large Array, the VLA in New Mexico, is as though it was a single dish 22 miles in diameter. But even the VLA is dwarfed by the radio telescope that you just saw in the video and is the workplace of tonight's lecturer. The Atacama Large Millimeter, submillimeter, array, or ALMA, is situated, as you saw, in Chile's high desert, a bit north of Carnegie's Las Campanas Observatory that you saw in the first video. The high, dry Atacama Desert has some of the best observing conditions in the world. As you saw, ALMA consists of 66 linked dishes designed to listen at the short end of the radio spectrum. It is the largest ground-based astronomical facility in the world. ALMA is a partnership of the European Southern Observatory, the U.S. National Science Foundation, and the National Institutes of Natural Sciences of Japan, together with organizations in Canada, Taiwan, and Korea, in cooperation with the Republic of Chile, which sends many of its astronomers to work there. So it's, as is true of many other telescopes, a very international partnership, particularly wonderful kind of thing. ALMA is led by our guest tonight, Pierre Cox, a French astronomer and a founding member of ALMA. He studied physics and earned his PhD at the University of Paris. He has been ALMA's director since the facility officially went online in 2013. So this is still very new technology and science. Before joining ALMA, he was the director of a French Institute of Radio Astronomy, IRAM, which operates radio telescopes in France and Spain. He joined IRAM in 2005 after earning his PhD and later served at the Max Planck Institute for Radio Astronomy in Bonn in Germany, and at the Marseille Observatory of the French National Center for Scientific Research. He's acclaimed for his research into star-forming regions, evolved stars, and high redshift distant galaxies. He has published more than 200 papers and been cited more than 15,000 times, 15,001. As director of ALMA, he coordinates an international team of astronomers from 4 continents. In ALMA's first few years, these scientists have produced a steady stream of amazing discoveries. And as he will tell us, as Dr. Cox will tell us tonight, the future promises many more discoveries of those kinds and new kinds. So please join me in welcoming Pierre Cox.
So good evening, everybody, and first of all, thanks to Matt for his nice words and his introduction, and also his nice introduction of the ALMA facility, including a very interesting new way of transporting antennas that I know that it may perhaps use in the future. It's my great pleasure to be here, to have been invited to give a public talk about ALMA and present the science and also trying to explain what ALMA is doing in front of such a great audience. And I hope I will be clear enough and entertain you as much as possible. So the title is ALMA in Search of Our Cosmic Origin, and the next slides will try to explain that line. So first of all, why Chile and why doing astronomy? Chile is in the south, the ALMA is in the northern part of Chile, and it's a wonderful place to watch the sky. As the image can show you, you have the Milky Way really on the zenith on top of you, and it's always shining there. It's a spectacular view. It's one of the most fantastic things I've seen, and it attracts all the astronomers to go there. And you should know that in about 10 years' time, 70% of all the capabilities of ground-based astronomy will be located in Chile. So one question people ask me sometimes is, why do I do astronomy? And so let me go now from a view of the Earth, but seen from space. And when I was a kid, I saw this picture, which is a famous picture of the Earth seen from the moon. And that really completely flabbergasted me and still amazes me today. And you may have seen this new version of the same view. But I think it is one of the most amazing pictures I've seen, at least, where you really wonder what that blue spot is doing in space and why is it so different from this, the moon, which is so desertic and so inhospitable. So those are the basic questions that at least triggered me and brought me where I am today. So what is ALMA? ALMA stands for the Atacama Large Millimeter submillimeter array. It is an array of 66 antennas, which has been conceived and built to observe the universe in the millimeter, submillimeter regime. So those are high frequencies, typically from something like 80 gigahertz to 1 terahertz. And it acts like a zoom array. It's called an aperture synthesis telescope. And the antennas are located at 5,000 meters altitude on the Chasnantaro Plateau, and that is 16,000 feet altitude in US units. And it is operated in a way where you can move the antennas, not in the way Matt described, but I will explain you later, from a very compact configuration where the maximum distance between the antennas is 150 meters to a very extended configuration where the size is about the size of Washington, DC, so it's about 16 kilometers. Just transform that in feet, if you wish. It is operated from 3,000 meters, where the technicians, engineers, and astronomers are living and working, and all the antennas are controlled from the camp base. It has been built to operate for 30 years. The end of construction was in 2014, and probably it will be longer, probably 50 years or even more. And that will be the ALMA for the decades to come. So this is a view of the base camp and where the antennas were mounted. This is an old picture, but I think it's a beautiful picture, which shows you also the landscape. And the next picture is an aerial view of the array, where you see the Lincoln-Cavour at 6,000 meters here, the technical building here, and then here the compact array and the 12-meter antennas around. It also is a nice picture which describes you the beauty of the landscape, and Chile is known as a natural laboratory for obvious reasons, for volcanology, for ocean studies, etc. And it's clear that the northern part of Chile is a wonderful place to do astronomy. This is another view taken by a drone where you have the 66 antennas with the compact array here. So what is ALMA doing? I don't want to give you here a lecture on interferometry, but one thing that I would like to explain to you is that the idea is to simulate a telescope with virtual size diameter, which corresponds to the maximum distance between the antennas. And if you think about a telescope of that size, let's say 16 kilometers, that's impossible to build because it will crash under its own weight. So the way to do that is to fill that virtual surface with smaller dishes. And of course, the more dishes you have, the better it is. And it's sort of limited by the amount of money you have to build it. And for ALMA, the number is 66 with 50 antennas of 12 meter that are spread around this 16 kilometer array. And the idea here is, as you see, you have antennas that are filling this huge surface, but there are many holes in it. So think about the antennas in terms of pixels. Now, when you observe a source, the source stays where it is, but the Earth rotates. And while it rotates, gradually antennas here are going to fill in the surface of the virtual surface of the dish. And so the idea is to use the rotation of the Earth to do an image of the source you're interested in. Of course, then there's a lot of technique where you combine all the radiation of each telescope, of each antenna, and you do interferometry, and you do all possible combinations between all the couples of antennas. So ALMA is a global project. As Matt said, there are 22 countries here involved. You have all the flags here. It's a project that started to be discussed in the late 90s and really in the 2000s. And it's a beautiful project that brought together 3 big regions doing that type of measurements, that type of science, and with different skills, different expertise, different backgrounds as well. And all that led to the wonderful project that is ALMA, with all its complexity. And I like this African proverb: if you want to go quickly, go alone. If you want to go far, go together. And I think ALMA is a wonderful illustration of the fact that when you're together, you go much farther, much better, and you're much more powerful than if you go alone. So what is ALMA doing, and why do we spend so much effort and time to probe the millimeter, submillimeter window? So this is the electromagnetic spectrum, where you go from the gamma rays here to the radio, and our eyes essentially see a very tiny bit of the electromagnetic spectrum that is emission, that is emitted by celestial sources. And astronomy, starting at the beginning of last century, really started to explore all the rest of the emission from the radio to the gamma rays. And ALMA is probing that part of the spectrum, which is a millimeter, a submillimeter. And as you see here, it is very sensitive to very cold emission. And if you look in the temperature here for the gamma rays, it goes to 10 million degrees Kelvin. And here in the millimeter, submillimeter, you go in the emission, you probe things which are 1K or 10 to 20K, so minus 272 degrees Celsius. So in a nutshell, what ALMA is doing is to probe the cold universe. To detect those wavelengths, as you can see, if you're at a sea level, most of the emission, except for the radio and the visible, is absorbed by the atmosphere for many reasons, because there is water, oxygen, and so on and so forth. But if you go to higher altitudes, then the transmission augments, and so that's why ALMA was built at high altitude, to probe that part of the spectrum that is still transmitted at these high elevations. So why in Chile? So first of all, as I say, the Earth's atmosphere absorbs part of the submillimeter, millimeter radiation, and you need hence to be at a high altitude and at very dry places. So there are not many places on Earth where this is happening, and this is a satellite picture from Aqua, which is 13 years of data showing the water vapor content, the cloud coverage on Earth. And as you see, there are not very many places which are high and which prevents very low water vapor content over years and years. There are 2 essentially. It's the northern part of Chile, which is in blue here, and the South Pole. Now, the South Pole is a great place, but logistically it's very complicated. And Chile is it's easier to attain. And also, as I always say, in Chile, at least you have very nice drinks like piscos, which you probably don't have in the South Pole. Why is it dry? It's because it's like a tunnel effect, where on the one hand, along the long coast of the Pacific, you have the cold currents from the South Pole that are caught here and that go along the coast. So the ocean is very, very cold. And then you have the barriers of the Andes, which blocks everything coming from the Amazon. And so at the north of Chile, you have this sort of long stretch of land that is very dry and harbors the driest desert on Earth. On the other hand, in the northern part of Chile and near the Atacama Desert, there's this huge plateau which extends over kilometers. So you have 2 things. You have a high plateau at 5,000 meters. It's very, very dry, and it's the ideal place to do submillimeter, millimeter astronomy with antennas that you can spread over the plateau. So this is the reason why it is located in Chile. So it is a very unique observatory, and it has two complex high-altitude places, at 3,000 meters and 5,000. It's isolated. We produce our own energy. The staff is working there and living there day and night. We observe day and night. It's very extended. It's a movable facility. The weather can be very treacherous and unexpected. We have two winter periods. That's the altiplanic winter and the normal winter. You have an active volcano nearby called Lascar, which normally is fuming very gently, but sometimes has interesting earthbursts. And there are earthquakes as well, and hence safety is very, very important. And also, the Atacama is not exactly a desert. It's also populated by indigenous communities. So they're called the Atacameños. They're there since thousands of years, and with a very rich culture, heritage. And we have, I think, a very good relation with them. And I think it's a pleasure and it's an honor to do astronomy with modern equipment next to a culture that is still doing astronomy with their own knowledge, their own equipment, and their own traditions. And this is not historical, it's still done and vivid, and I think that the two coexist is wonderful. This is a picture taken just before the inauguration, where the Atacameños bless the Earth for the good of the project. So what is ALMA doing, and why is it interesting to probe the cold universe? So this is a picture of a starry spot of the sky, except there is this very dark thing in the middle. And Herschel, the great Herschel, wrote to his sister Caroline Herschel when he detected these very dark spots in the Milky Way. He said, oh, in German, hier ist wahrhaftig ein Loch im Himmel, which means really there is a hole in the sky. And what is this hole? It's not a hole, in fact. It's full of matter, which blocks the light of the stars which is behind. And it is essentially composed of dust. And dust is blocking the radiation of the stars. And what you see there is a cloud of dust and gas that is collapsing and forming the next generation of stars. So if you look at the composition in the universe, most of it is hydrogen and helium, but you have a few percent that is composed of dust, and another few percent that is composed of all the other molecules and whatever that is shaping ourselves and this public audience that is listening to what I'm telling about the composition of the universe. And then, of course, dust, sure, it's beautiful, but I can't help thinking about all that interstellar dust out there. And but it is indeed very beautiful. ALMA is not only measuring the cold dust, but also has a unique way of probing the composition of the clouds and the molecular content. Most of the molecules emit their fundamental transition in the millimeter, submillimeter range. And so it is really a field that opened up what is called the astrochemistry. And each molecule has a perfect, well-defined signature. And when you have 2 or 3 lines, then you can identify the molecule in question. Today, about 200 or more molecules have been identified in the interstellar medium, and I will comment upon that further on. So ALMA probes the cold universe, probes the dust, and probes the content through the molecular content of these clouds. So why is it important to do astronomy at different wavelengths? It is because the things like a galaxy are very, very complex objects, and so complex that you need the whole full electromagnetic spectrum to understand what it's all about. So this is a galaxy Centaurus A seen in the optical. You see, by the way, these wonderful dark clouds here, where the next generation of stars is being formed. This is the view from an ISO, I think, so an IRIS, an infrared satellite seeing the radiation of the dust heated by the stars. This is a view seen by ALMA, where you see the molecular gas in these clouds. This is the same galaxy, but seen in the radio, where you see the jets coming out of the center of the black hole. This is the hot gas seen by Chandra. This is done by the VLA here. And this is the composite picture of this galaxy. In other words, to understand what is happening in this complex object, you really need to go all through the spectrum to really probe the different physical and also chemical conditions and processes that are happening in this galaxy. So to do that, of course, you need a very cutting-edge technology, and ALMA is a wonderful facility with a lot of cutting-edge technology, and I don't want to go too much into the detail, but give you a couple of examples. The ALMA antennas, for instance, there are 66 of them. There are 3 different antenna manufacturers and 4 different antenna types. You have 50 antennas that are so-called baselines, 25 which are built in the US, and 25 built in Europe. And then you have the compact array, which is done, the 16 antennas, 4 which are 12 meter, and the rest are 7 meter antennas, for a reason I can explain later. But the most amazing thing here is that all these antennas, although built by different builders and manufacturers, have the same specification, and particularly very, very high precision, which corresponds about to a knowledge which is better than the quarter of the width of a human hair over the whole surface. Each antenna has receivers. Today there are 8 receivers on each antenna, and they're covering all the wavelength range from about here, from here. So it's from 80 gigahertz up to about 900 gigahertz or above. Here are the details of all these bands, and currently there are 2 bands that are being constructed. One is the lowest frequency band that's being constructed today, and the last band, which is being discussed and will be probably installed in the next coming years. So the equipment and the data flow between the ALMA regions is a whole chapter in itself, and the data is being taken in Chile, is sent in the US, in Charlottesville, in Isia and Tokyo, and then in Europe in Garching. And then when there are big problems with some of the components that needs to be overhauled or being looked at, then they're brought back here, and so there's a flow, a current, really ongoing flow of people, of material, of IDs and data between the Northern Hemisphere and Chile, where ALMA is. Along the way, there are sometimes exotic encounters, and this is a piece of antenna that was brought to the site, and you see the llamas here in the Atacama Desert. When I said it's a movable feast, so the antennas are not transported at the mat type of transportation. They're not lifted. They are transported with transporters, trucks, that transport the antennas from the lower side when needed to the upper side. So this is the way to the upper side. This is a view where you see the intricate network of roads on the site. It's an earlier picture. And then the antenna is brought into the array. And to change the configurations, you do the same thing. You pick up an antenna and bring it to one of the 992 paths that are spread around on the Chasnantoro Plateau. By the way, Chasnantoro is a Kunza word, Kunza being the language of the Atacameños, and it's called the land of departure, which I think is a very nice name for an observatory. So what is ALMA doing or will do? So ALMA started to do science 5 years ago when it had 16 antennas, and gradually antennas were brought into the array, and did science immediately at the highest possible level and transformational science, and has not stopped since then. I think ALMA is so powerful that whatever it does, it opens up a completely new window into the objects that you're looking at. And it really covers everything from the formation of galaxies billions of years ago to the formation of stars and nearby galaxies in our own galaxy, formation of planets and stars, but also the chemistry of clouds and new solar systems. And all that is done from nearby to very, very far away. So ALMA has produced so many papers. There are about, I think, 1 paper now per day, which is published based on ALMA data. It's become very difficult to make a selection of what one want to present to a public like this one, and to make a selection. So some of them are based on my personal interest, and I will try to give you a flavor of what ALMA is doing, although it's clearly not a complete picture. Let me start with very close by, the solar system. Despite the fact that you have satellites that are visiting all the planets nearby, ALMA is still a very, very interesting instrument to measure all the other things that are supporting or providing complementary information to what the satellites are doing. So as you can see here, for all the planets and also the outer bodies and the belt ALMA has provided key signs in many of them. So let me start with a first example. I said a few minutes ago that ALMA has been built to study the cold universe. So there's one exception, is that the sun is not really cold, but ALMA is able to measure the sun. And it was built and since the beginning to really be able to study the sun without burning the receivers or burning the surface of the antennas. So this is a picture of the sun in the optical in the H-alpha line, and the same day, and this is a picture of ALMA, obtained with ALMA at high frequency with one telescope. So that was done in 10 minutes or 15 minutes. So it's a mosaic of the whole sun. And as you see there, you see all the spots here. And the interest of ALMA is that with these wavelengths, you are probing a region that is not very well known, which is just at the base of the corona, which is called the chromosphere. And this is now an interferometric image, so high spatial resolution of one of these spots here. This is the ALMA image. And this is one image obtained at high frequency, and this is an image obtained at a lower frequency, so at lower temperatures. So you see that there are differences in the morphology, and that provides you a measure of the temperature in the chromosphere at a way that hasn't been seen at that level of detail before. Another interesting result is the asteroid Juno. I show this because it's obtained, it was one of the first results obtained when the long baselines were used for ALMA. And the resolution here corresponds to about 60 times 45 kilometers. Juno is orbiting between Mars and Jupiter, and this is a fantastic resolution. And here's here's the ALMA image, and here's the model, and it's I think it's a testimony about how precise ALMA is even for the very small bodies like asteroids. Another very nice example of what ALMA can do in the solar system is to position or measure with great precision the positions of celestial objects. And this was done for the Pluto and Charon couple, where I was asked soon after I arrived and took the responsibility of the ALMA director, if ALMA couldn't measure more precisely the position of Pluto. And I was flabbergasted that that wasn't known precisely enough for that mission, which was New Horizon. And so we did the measurements over many months and finished with an accuracy that corresponds at the distance of Pluto of about 100 kilometers. And that enabled the New Horizon mission to slightly correct their trajectory to be more efficient, save fuel, and after the flyby of Pluto, which everybody has seen here, to go beyond that and explore the Kuiper Belt object. So here is a nice example of ALMA supporting a equivalent type of 1 billion whatever mission, but in space. Now let me go to the next big chapter of what ALMA can do, and where ALMA was built, is to understand how stars are formed or planets are formed. So this is a schematic illustration of a gravitational collapse of one of these dark clouds that I showed before. And so the matter collapse, and gradually in the center, you are starting to form a star, which is then ignited by nuclear reactions, and forms a star with a lot of activity, bipolar flows here, forms a disk, and then the disk is rearranged in ways that are still not completely understood. Planets are formed, and finally you have a central star with orbiting planets around it. So in all these different phases, ALMA is seminal in trying to understand what is happening in all these phases. So the other thing is to understand how you form planets from very, very tiny dust grains. So micro-sized dust grains that are growing into millimeter-sized grains, then meter, then kilometers, and then planet-sized. So ALMA is very good in probing those very tiny grains and the millimeter-sized grains. There's a big gap here, which is a big unknown, and how you go from these grains to the bigger ones, and then how planets are formed. So I will show you what ALMA can do in these things. So this is a video which shows you the collapse of a cloud. It's a model. And gradually, you have a flattening of the matter. and you have the appearance of a disk that is spiraling faster and faster, and then you create here at the center a star, and then you have matter which is organized around this in sort of spiral arms, and it's more and more complicated. And I don't know exactly what the conditions were, but you see that all these models predict spiral arms and etc. deep into the cloud. Those things were never really seen, and ALMA, I think, has shed fantastic light on these processes. So let me now go from that's very technical, but I think it's a wonderful example of a cloud that is collapsing, and it is collapsing very slowly with a mass inflow of about a few 10 to the minus 6 or a millionth of solar mass per year to the center. And what you see here is the cloud and the continuum, and then you can also look at the molecules and the dynamic. So this is very technical, but essentially what you see here is that there is an absorption feature against the continuum that is redshifted. And that is an ambiguous evidence of infall towards the luminous source. And it's one of the best evidence ever measured of a cloud that is contracting and forming a star toward the center. So once the star is formed, you have all these activities going on. You have jets, and this is a nice example of a complementarity between the millimeter observations and the optical. So this is an optical image where you see a dark cloud, and here sort of a star which is here, which is ejecting matter into the interstellar surroundings. And if you look with ALMA, the same object here, these are the ALMA data, and you really deeply look into the cloud, and you have a full picture of the outflow of this young star. So young stars are very active, and for reasons that are still poorly understood. And this is a very nice example. You have a young star here that has been formed recently, and that is ejecting at a bipolar outflow here matter in the interstellar medium, which is then colliding with the surrounding gas. And here is a velocity presented map where you have here the gas approaching you and here receding from you. And what you see in this image and the next one is that you have episodic events of outflow where the star is sort of popping out gas now and then very regularly, and there are up to 11 events here that have been measured. So this is a wonderful way to understand how these stars are active. Not only the low mass stars are active, but the very massive stars are also very active, and that's very difficult to measure. Luckily enough, we have very close by a nebula called the Orion Nebula, which is shown here in a near-infrared image obtained with MUSE on the Very Large Telescope from ESO in Chile, which is a composite image of different lines, iron and molecular hydrogen. And here you have the trapezium stars, and here you have located a very well-known source, which was one of the brightest infrared sources in the sky, called the Beckling-Nagelberg object, BNKL. So let me show you what is happening around these young stars here. And this is an image that was obtained with Gemini South in molecular hydrogen and iron. The young sources, the massive stars, are here. And you see an enormous array of incredible ejections, fingers, that seems to be coming out of the center of where the stars were. And of course, this is an integrated image where you have no information about the velocity. So ALMA has measured the same region recently, and what you will see is an image in carbon monoxide, including the information on the velocity. So this is the image, that's the integrated image. You have here at the center, you have all the sources which are identified with arrows indicating what directions they are moving and the position they will be in about 2,000 years. It is thought that all these sources were 500 years ago here where the cross is, and sort of dispersed when it was formed. And what you see coming from the center here is an array of incredible complex sort of fingers and outflows in all directions. So the next image shows you the same image in the background in green, and here in red and blue you see the blue redshift and redshifted gas, and here you only see the blue and redshifted gas. So it's like a big flower where all these young stars, massive stars, were turning around each other for reasons that are still unknown, a very turbulent medium, and ejecting these episodes of mass in opposite directions while they were evolving. Now let me go back to this picture and show you what young stars do to their surroundings from which they were born. In other words, what is the influence of a radiation of a young formed massive star, and the UV radiation just eats up the molecular cloud from which it was born. So I will show you an image obtained with ALMA of that portion which is called the photodissociation region of Orion. It's a bar where the emission from the trapezium stars is just impinging and sort of gradually eating into the cloud. And so the next picture is the same little portion here, where you see in red, it's a molecule HCO+, done with ALMA and combined with data from the 30-meter telescope in Spain. And here in blue and in green, you see the ionized gas that is gradually eating into the molecular cloud. This is a wonderful picture. I think it's the first time ever that I saw a molecular cloud that really looks like a cloud and not like contours. Now, let me now go to the next stage, which is the matter that is organized around young stars. And this is not ALMA. This is the best that was done before ALMA. This is a series of young stars where you see from different measurements done with CARMA, with IRAM, so the best things doable, where you see matter around these stars here. This is continuum emission. This is dust around these stars. That clearly has, for instance, here a shape of a disk, here as well, and here as well. But they're contours, they're blobology. The next picture is what ALMA is doing. So you see the real enormous leap forward due to the facility of ALMA. And what is also amazing in this series of pictures is that there is no such thing that resembles the others, and they're very different. You have spiral structure here, you have very sharp gaps here, less pronounced here, less here, and then you have a very complex structure here, which I will comment upon later on. So this is really ALMA opening a completely new view about what is happening around a young star and how the gas is arranged around that young star. To put that in perspective, so this is an image, I go back to HL tau. The next image is the ALMA image compared to what the Hubble Space Telescope sees in blue. And what you see with the Hubble Space Telescope is a sort of a cone of light that is the diffusion of the central star on the dust and the cloud where the star was born. And with ALMA, you probe into the cloud and you really see the disk around a young star as it is formed. So the complementary here is obvious. So in terms of what it really means, I think the jury is still out. But there's a lot of indication that what you see here is the gaps are caused by planets. And if there are planets in this case, they're below a Jupiter mass of so. So these are models, and as you can see, the model represents very well the observations and very closely so. But there can also be all sort of chemical effects about how these gaps are formed. This is the complicated structure I just saw, and long story short, it's a triple system, 3 young stars formed in a disk here, and hence the very complex structure that has been also modeled, as you can see here to the right. In disks, you have also chemistry going on, and not only dust, and there have been very interesting studies, in particular this one, where in this protoplanetary disk, methyl cyanide has been found, and with an abundance that is very akin to what is found in our solar system. So it is very clear from these observations that there is a common pattern here between when a star is formed, the planets are formed, and the chemistry that is evolving from these matter. So cyanides, of course, are important because they contain the carbon-nitrogen bonds that are essential for formation of amino acids, and which are the foundation of proteins. So chemistry is one of the biggest, I think, topics for ALMA. And let me go through here recent results. I mean, one of the biggest issues when you have a cloud that is collapsing is you have ices around the dust grains that are formed on the surface of the grains, and the ice sublimates because of the dust, the radiation of the star, and then they're formed again on the surface of the grains here. And all that complex chemistry is still untapped and not really understood. So there's a close by region of star formation called the Rho of Fucus, where there's a little source here, which is here, a double source, which is shown here, which is very, very interesting, in particular this source here. It's a very young star, and where very complex molecules were found. And particularly here, this is a detection of sugar, glycolaldehyde, and that was found in this particular source. So that source has caught a lot of attention because it's nearby, and many things were discovered. And recently there's a project with ALMA where it's an unbiased spectral survey of everything possible given in a certain band in here from 330 to 363 gigahertz. And it has a sensitivity which detects species that have abundances which are about 1/100th relative to methanol, about 10 to the minus 11, 10 to the minus 12 relative to molecular hydrogen, which is the most abundant molecule in space. So this is an example of what is being done here. And keep my word for right, there are more than 10,000 spectral lines in that spectrum. So it's really difficult to disentangle, identify all these lines. It's being done as we speak. A few percent from the small non-organic molecules are contained there. There are known saturated organic molecules and isotopic variants. So it is really a treasure trove here where you can really find molecules that are not abundant, but are very complex. And to give you an idea about the complexity of the molecules, you see that acetone, propanol, acetylenediene, and ethanol oxide have been found. And the detection of these complex molecules were only seen previously in very distinct sources, but not in a protostar. And the isomers are also important for testing chemical models and laboratory experiments. And here are the depictions of these different molecules. So ALMA is looking at how stars are formed, how planets are formed, and then the chemical complexity, the complexification of the matter as all these things evolve. So how is the interstellar matter replenished regularly by dust, and how is dust formed, and how is also the elements out of which all these things are made, how is that made? So one of the biggest factors of dust in the universe is the so-called asymptotic giant branch stars, AGB stars, which is the fate of all solar mass, stars of a few solar masses will all end their life in AGB stars. This is one recent example of such a star, which is a star which is losing mass at the end of its life. And it's a binary star, and what you see here is a star which is losing mass, turning around another one with an orbit with a high eccentricity, and so making these beautiful spirals on the sky. This is a composite image of ALMA and the Hubble Space Telescope. And not only that, but you also have the velocity. And so the matter is ejected at about 10 kilometers per second in space, which is not much for these sort of ejections. And those are frames where you see different settings in the cube of the velocity. I just played again here. That you see, there it is, and you see the different gradual projections along the velocities of that star. So another way to make dust, which is poorly understood yet, but I think this is a beautiful example where it has been constrained, is for stars that are much more massive than our sun, so tens of solar masses, and that explode in supernova remnants. And this is a famous supernova remnant that exploded 30 years ago, in 1987A, in the Magellanic Cloud. And this is the famous Hubble Space Telescope picture, and the Chandra here, where you see the shock of the matter from the explosion that is impacting the matter that was ejected by the star. This is the ALMA image, which is an image in the continuum, which is a direct measurement of the dust that was formed 30 years ago. And what is important here to notice is that the amount of dust that is estimated to be formed in this supernova is about a third of a solar mass or so. And that's very important because it gives you a measurement of the yield of the formation of dust in supernova remnants, and I will comment on that later on when I go to the very early galaxies formed in the universe. Now let me now go to extragalactic astronomy and jump immediately to the black holes. This is a recent example of not a black hole, but it's a gas that is seen in a cluster in a galaxy called the Phoenix cluster. And you see here like a tunnel or like a funnel of cold gas, molecular gas. And this is the image of Chandra. And what you see here is a very hot gas with bubbles that are ejected or created by the activity of the black hole here in the center. And what you see here is that the molecular gas found by ALMA fits in exactly and is sort of funneling that ejection in these bubbles as shown here in this artist's impression. So black holes are really an important subject for ALMA. And ALMA is also able, through interesting techniques, to measure the mass of black holes indirectly. And this is an example in the spiral galaxy NGC 1097, where our Japanese colleagues have measured in the center here, around the black hole, the molecular gas that is distributed in a ring and that is circling around the black hole. And the dynamics of that ring provides you an estimate of the mass of the black hole, which in this case corresponds to 140 million times the mass of the Earth. So as you all know, it is also clear that our own galaxy has a black hole in the center in Sagittarius A star. And one of the very cool potential results of ALMA, which I don't have the data yet, but I just will make some publicity, is to measure and to image the black hole of our galaxy. And the way to do that is not easy, because even with 16 kilometers, even if that gives you a higher angular resolution, that's not sufficient. So to do that is to go and ask for, to combine the ALMA data with data taken in other places, not in the universe, but on Earth, and to combine, looking at the same source, different telescopes located in Hawaii and the West Coast with ALMA here, and then with the South Pole telescope, and then also with Europe. And there you don't have baselines of 16 kilometers, but you have baselines of 10,000 kilometers, providing you exquisite angular resolution. And of course, I mean, you're losing a lot of temperature brightness here, but if you have sources that are strong enough, you can do that. It's called a technique called VLBI, Very Large Baseline Interferometry, and ALMA has joined the network of VLBI recently, offering to the community to do it both at 3 millimeter and 1 millimeter. So the angular resolution is such that you can distinguish a ball of golf on the surface of the moon. So the idea here is to make an image of the black hole, the event horizon, so the surface around the black hole in the galactic center. This is very much model dependent. Those are two different models here. And we don't know what we're going to see, and we hope that we're going to see something. And so in March, the measurements will be done with many telescopes that I just showed here. And so stay tuned for these results to come out soon. Another nice example, and then I will go to the very high, oops. So sorry, but this didn't work. So let me go to the high Z universe then. I had a beautiful image there, but of interacting galaxies. So one of the big advances of recent astronomy, I think, is that we are currently able to really probe into the early universe and understand how galaxies were formed. There are many questions that are still pending. And here is a little cartoon giving you numbers and ages from when the first galaxies were formed about 1 giga-year after the Big Bang. And then you have the galaxy build-up more than 1 giga-year later. And then you have today's universe and people like you listening to somebody explaining how the universe was evolving. Along that path, there is the structure formation and how the galaxies grew through gas accretion. There are a lot of questions that are being unanswered. And the idea is to really probe and understand the physical conditions and understand how these things work. So to do that, there are many ways to look at the early universe. And one of them is to use the effect of gravitational amplification, where the more you look, the more distance you look, the more it is likely that you may encounter on your line of sight some very massive galaxy that acts like a lens. That was an effect which was predicted by Einstein in the general relativity. And so what happens is that the source, which here in the back, is distorted and amplified in such a way that you're able even to detect galaxies that are very weak and very far away. So that was done, I think the first detection was in the radio in the centimeter probably 30 years ago. And this is an example of ALMA where you see in blue here the Hubble Space Telescope foreground galaxy that is amplifying, and then right here the distorted galaxy for the background. So one of the nicest results I have seen from ALMA, and I may be biased because it's my field, but is the following example. This is not ALMA, this is a deep field obtained with Herschel, where you see really literally thousands of galaxies in the background, all at high distances. If you look carefully, you see that there are some of these points that are much more brighter than other ones, and those are tentative candidates for being magnified. And indeed, all of those have been found to be magnified. So let's concentrate on this little dot here called ID 81. And this is located towards a very massive nearby elliptical galaxy, which is seen here. That's a Hubble Space Telescope. And exactly here at the center, way, way back, the redshift corresponding to when the universe was about 1 gigahertz after the Big Bang, lies a galaxy inconspicuous. But if you look through this lens, then it's magnified and produces this ring. So this is a ring where there's lots of emission that has been piled up. It's done with the longest baselines of ALMA, and it's emission from dust, emission from carbon monoxide, but also emission from water. And what you're looking here is the distortion of this galaxy, and then you can model it again because you know what the distribution is of the foreground galaxy, and then you can, depending on the models, this is the view of that galaxy very, very far away. So what I find amazing in this is that the scale here, you can distinguish structures that are about something like 200 parsecs or so, which probably doesn't tell you anything, but this corresponds to giant molecular clouds in our galaxy. But seen here in a galaxy which is seen when the universe was very, very, very young. So probing further, you can also do deep fields with ALMA, and this is one of the first examples of a deep field. This is the Hubble deep field in blue here, and in color, in orange, you have the equivalent seen with ALMA to a certain depth, and it is a spectacular result, but it will be even more spectacular when more time will be spent to have even lower or less intense galaxies and populate the whole picture here. And then let me finish with two examples. This is a very far away galaxy when the universe was about 6 or 10% of its age, where you see a blob here. And what is interesting is that people looked for dust, very conspicuous lines that are dominating nearby galaxies like ionized carbon or carbon monoxide. Didn't either detect the dust nor that, but detected a line of oxygen, ionized oxygen, which is a tracing a very, very highly excited gas around the stars that are formed. And I think that is interesting because it provides new means to really probe the early universe. And this is the currently highest redshift galaxy found with ALMA, which is shown here, a little blob here. It is the highest one as of today. It's at the redshift of 7.5. But stay tuned, tomorrow there will be a press release. It's embargoed, so I can't tell about it. But it's much farther away, and you will be baffled. So let me finish with this beautiful image. I think what is really amazing is that in the 5 years since ALMA started operations, is that ALMA already achieved most of the fundamental goals that were set 15 years ago that really supported the whole ALMA project. Here are the 3 goals. It's to detect emission from molecules like CO, atomic or ionized gas, in a galaxy at a redshift of 3 in less than 24 hours. That has been done successfully so. Then the ability to image gas schematics and protostars and protoplanetary disks, and enabling to study their physical, chemical, and magnetic field structure. That still has to be done. To detect the gaps created by planets. I think that was done successfully so. and then provide precise imaging with very high dynamical range. So I think it's quite amazing that when ALMA was still being built and when antennas were being brought to the site and incorporated in the array, that ALMA really achieved these fundamental goals set 15 years ago. So let me here finish. Thanks to all the ALMA partners and staff, some of them present here, and most of all, thank you for your attention.
Okay, so we could have the lights up and we have time for some questions. There are 2 microphones there and you can get in line at either of them. Or if you're really fast, you can get in line at both of them. And we'll welcome some of your thoughts.
You mentioned how the design specifications had a very precise shape. How difficult is that shape to maintain as there change positions and thermal changes over the course of a day?
So, I mean, there are, I mean, we do regular panel adjustments and I mean, measuring the surface of the dishes to improve that. But you're right, I mean, and particularly in these harsh conditions and temperature changes or whatever, that affects somehow the surface. So we are trying to do whatever we can to keep that precision as high as possible. And currently we have done, I mean, one thing we discovered recently, for instance, that we did panel adjustments for instance, at 3,000 meters and then brought the antennas up to 5,000. And then discovered that that wasn't good enough because there were changes. So what we're doing now is the panel adjustments at the 5,000 site, 5,000 meter site to keep the same conditions.
I don't know whether this exactly fits in with what you've described, but it's a question that's been on my mind that I'll throw out there and see what you...
Hope you can answer.
Okay. Yeah, maybe you can't, but so what? Recently with the Higgs factor, now that they know the particle, are you aware of what's going on there?
With ALMA?
No, but is there, with the Higgs particle?
Yeah.
Maybe I shouldn't ask this. Okay, with the Higgs particle now, they've been able to come up with the size of it and the weight of it and so forth. And what they say is that at one end, that it would indicate a multiverse probability, and at the other end of the weight possibility for the Higgs particle, it would just be our universe. So my question is, how deep can you look into the materials you're looking at? One, to see the possibility of a multiverse, and two, why is the size of the Higgs factor a determining factor or an indication of whether it's multiverse or one universe? Is that anything to do with what you're working on?
So that's a very difficult question. I'll try to answer that. I don't think that with ALMA, because let's stick to ALMA, that we can have any sort of indication about universe or multiverse. And although I mean these questions are very interesting and debated today, I think that as an observer and certainly as a director of ALMA, we are in the middle of one universe, which we are, we are there. And there's this very famous picture that I think Camille Flammarion did in the 19th century, although it looks like a picture of the Middle Ages, where you have an astronomer looking through the globe of stars and looking behind that. Right. So I don't think we are in a position to do that, although it's very dreamy. And the best we can do is to really understand and how, the history of the universe, and also what the matter is. I mean, one thing I didn't say about the ring that I showed before, that is a very interesting indication that if you do model that ring very properly, that you see that there is something that you cannot explain very well. And the only way to explain it is that what you see is that it's an amplification through a sub-halo of dark matter. So ALMA may be used in the future to do these very exquisite high sensitivity measurements of galaxies that are amplified by very massive objects in the line of sight. And then with the exquisite details of ALMA, you can sort of find out indirectly the presence of that type of object. So I hope that answers somehow your question.
Okay.
Yeah.
Thank you for trying.
Thank you, Dr. Cox. This was wonderful.
Thank you.
As myself, I'm a social entrepreneur, so I'm trying to design business solutions to our social problems. And then when I see this, it is so humbling. It makes me really question how silly all of our problems are. Very silly, and at the same time, it was very inspiring. Of course, the stars, but also the way you're collaborating with the science community all over the world. Why can't we do that when it comes to poverty and all these things? I'd love to kind of get your perspective on how can we teach this kind of broader perspective to people so that we can unite and work together as one human race?
I think I can only applaud your comment and certainly profoundly agree with what you're saying. I mean, I see that you were quoted by my African proverb, and I think I agree with you. What I really like about this project is that it is a common adventure, endeavor with a vision and a common goal, with very different backgrounds, cultures. It's very complex, but it really works because everybody wants to have this working well. And I think what I showed there is it's successful. And so when you bring all these energies, these talents together towards one goal and organize it well, then it's a real pleasure and it works. So I wish you all the best.
Okay, over here.
The detail that you have shown us is certainly very informative scientifically, and it's beautiful and all that. Do you have any favorite scientific surprises, things you didn't really expect?
So clearly, I mean, one of the great moments in my tenure as ALMA director is when I saw for the first time the image of H.L. Tau that I showed before. When I saw it first, I mean, the deputy director of ALMA, Stuart Cordott, sent me the picture, and it was a Saturday afternoon. And for about 10 minutes, we talked on the phone, but when I say talk, it was rather like, whatever. If you excuse me, it looked like phone sex rather than anything doing with astronomy. And I'm still, each time I look at this image, I am equally amazed by the beauty. And it's sort of prefigure, it's sort of an opening also of the field. So yeah, I think that image was certainly a great moment. But there were other ones, absolutely. There's a lady there.
I'm an artist, and I wonder, I liked some of the slides you showed so much. I wonder if they're available online, if I can find them.
I mean, certainly, I mean, everything I showed is public, and I will be glad to put that online and make that available to you, absolutely.
So I could just go ALMA.
If you go to ALMA, there are many, many other images that are even more beautiful. And,
oh, well.
And I agree with the previous speaker. I'm very encouraged by how all these different observatories across the world and in the atmosphere are cooperating. So I know that the James Webb Space Telescope is hoping to launch and be operational within the next few years.
Yeah.
I'm not exactly sure on the time frame. Sometime around then, yeah. But do you know what the resolution of this telescope will be like compared to the array at ALMA, and do you look forward to working with the results that they'll be getting?
I think basically with the James Webb telescope, as also with the HAST, what I say, during my talk is that what ALMA is doing is complementary to what the optical telescopes are doing from the ground or from space. And so with the James Webb telescope, there will be an exquisite angular resolution, which is comparable to the best angular resolution you obtain with ALMA, depending on the frequency. And so that's very, very complementary. And I'm very much looking forward to when the James Webb telescope is launched and working, that there will be common programs or fields that will be done both with ALMA and the GWST. And I think, stay tuned for, I think, fantastic science to be done.
Thank you.
We have a question from Maxine Singer, former president of Carnegie.
I have a question. I know what dust is in my house. But I don't know what the dust is that you talk about and your colleagues talk about. Is it a word that you use because you don't know what it is? Or is it really something?
It is, it is really something, and there's a lot of it. It's a lot of cleaning. So the dust, there are different flavors, and we can give a whole hour talk about what dust is, interstellar dust. But essentially, there are two flavors of dust. It's like silicates, what you find along the sea. Like silicates and grain, salt. And the other one is carbon, and so carbonaceous compounds. And so small, fluffy, like platelets of carbon, up to fluffy particles and more compact things, and micro-sized sort of structures. The composition of the dust is very complex. The surface of the dust grains are very complex as well, and are very, very important in the whole life cycle of the interstellar medium matter, because it is on the surface of the grains when molecules stick and when it's very cold that you get all sort of chemical reactions and can produce all sort of complex molecules that you wouldn't produce in the very tenuous interstellar medium where the densities are so low. So dust, although it's only 1%, it plays a vital role in the cooling and the chemistry and the formation of ice, etc., etc. And then it grows and makes things like planets at the end. But essentially, it's not very far away from what you are dusting away in your own home.
Some of it's far away. Okay, so I have a couple of comments. I wanted to thank Margaret and Will Hurst for their generous support of tonight's program. They are the reason we have Fora TV here making really beautiful recordings of these lectures, which you can view on our YouTube and Facebook sites and on the Fora TV site, so very grateful. I'd also like to thank many of you who made donations when you were registering for this meeting. You may not know that we've been hosting these, I haven't been, Maxine's been here for about 27 years of these lectures. Pretty amazing, and we'll continue to do so. We'd love to get your input on tonight's talk, other talks we've done, and on things we could do in the future. We'd like to hear more from you. We'll be sending out a survey to collect your ideas, future events and topics you might like covered, and you can tell me about them. Tonight's lecture was the first of 5 that make up our spring lineup. We're doing some significant renovations in this building, mostly hidden from you at the moment, but you are breathing outdoor air in here for the first time since 1935. So we're very happy about this. Okay? And we will continue to improve this building in a number of ways. So our next lecture is going to be on a somewhat different topic, with Elaine Ostrander talking from the National Institutes of Health, not far away, talking about dog genes tell surprising tales. Oh dear. Understanding the genetics of breed, behavior, shape, and disease, and you can see some of the other upcoming talks listed here. I think you'll find them really fantastic, and registration is open for this next one already. We already have a lot of people signed up, so please sign up. And I hope you'll join us for all of these. We'd love to have you. And so let's once again thank Pierre for a wonderful talk.